Good evening, everyone. I really like building robots, so I wanted to spend some time telling you about robots today. My name's Morgan Bell. I'm a software engineer with a company called Sphero. A little bit about Sphero to start with. We were founded in 2010. Two guys, Adam Wilson and Ian Bernstein, got an idea. They wanted to do something fun and creative with technology, so they created this robot ball thing. And it was new and nothing really did something like that, so we ended up going through Techstars. It was an accelerator to kind of get the business side of the house figured out and to get that happening. And that worked really well. We picked up a Rockstar CEO, and then shortly after that, we went through the Disney Accelerator program also. And I'll tell you about that in a sec. A couple things that we actually build. When we first created Sphero, we actually had a test application that we created to do little macros. And we didn't think anything of it, but people kept asking us to do the same. Can you make the ball drive in a square? Can you make it the lights blink, whatever? And so we created this test app to do that, and it turns out it really works well for teaching kids to write code. So it wound up founding our Spark program, which is in about 10,000 schools worldwide. We went on after that and followed that up with BB-8. Everyone's pretty familiar with BB-8. When we were going through the Disney Accelerator program, we were approached by Disney, and they kind of said, well, you got that cool ball. Can you put a head on it? And so we did. We can make about 28,000 BB-8s a day right now, which is pretty cool. The manufacturing facility loves us. We've shipped about 2 million robots globally so far. So we've been at this a while. We thought this is pretty cool, but what happens if we want to make a more sophisticated robot? What if we want to make something that does more? And we've gotten a lot of lessons from the things we'd already made. Things like BB-8. People loved him because he had so much character and he had so much personality, and we thought, well, let's see about making a robot that's a little bit more interesting, that's a little more than a toy. So we started thinking about what that's going to take and how we're going to get there. We wanted to build a more cognitive robot rather than a control system robot like we have historically made. But we're really good at control systems, and we know that in a robot that's going to be necessary. You're not getting out of that. So we needed a lot of low-level real-time control. And it's real-time, not like SQL Server real-time. I need things in the order of microseconds, not in the order of minutes. The other things we really needed to have was GPIO that worked. We needed SPI, I2C, UART. These are just things that you need in a robot and you need in a real-time system. And you need those for things like sensors and PID controls. It's typical distance sensor, like an ultrasonic sensor, time of flight. You've got really specific timing requirements around how you read those sensors, and those are in nanoseconds or microseconds, depending on the kind of sensor. And then PID controllers have the same problem. You need precision real-time corrections to ensure that set points are held. We had that. We knew how to do that part. We could go get an M4 off the shelf and make it work. That was less difficult. What we really didn't know at the time was anything about the intelligence of the robot. How do you build a robot that makes decisions? How do you build a robot that has a psychology to it? It's much different than just a control system problem. And we needed to create something that was extensible and maintainable, and we could create a lot of deep, rich functionality on that. So we shopped around for a while, and we wound up buying the Dragon Board 410C from Qualcomm as our prototype platform. And we reached out to our vendor and said, hey, how do we start working with this? So they pointed us at their standard Linux distro that they use to do this kind of work. And as good roboticists are, we converted all of our stuff to Linux, and we started building a robot. It didn't go swimmingly. We learned really quickly that building your own BSP takes a lot of time. You've got several hours of compile time to get it to come together. And then when we finally did get it to come together, we wound up in a situation where Wi-Fi wouldn't work, or when we turned Bluetooth on, the SPI would stop working, and interrupt problems and configuration issues, and. We soldiered on for a couple of months at that, trying to build a robot with that system and make it work. And we were pretty well ready to throw in the towel, and a contact from Microsoft reached out to us, and they told us about this Windows IoT Core thing. It was really new, but it supported the 410C, and so we figured, well, we're already really frustrated. We might as well try it and see what happens. It cannot get worse. And it didn't get worse. It actually got better. A lot of the communication protocols just worked out of the box. There was no magic to get it all working. You just uncanned it. There was actual documentation managed by actual humans who write documentation. Everything was also based in UWP, which was a forward-looking platform. There's a lot of new technology being sunk into it, so we were really hoping to leverage that. They also had sample code and real sample code for interacting with real devices like you use in the real world. It wasn't just about blinking lights. It was about actual samples that did things. If I needed to read an accelerometer over I²C, there's a sample for that. The other thing that was great was having excellent tools. We worked really hard to build up a tool chain under the Linux environment to try and manage and deploy the code and make it all come together. And it was honestly, it hangs together by sheer force. Having Visual Studio and just the ability to deploy things naturally, it really smoothed the process out. So what happened next was pretty cool. We started to actually make progress building our robot. It wasn't just a dream anymore. It was the kind of thing where we started to get things to hang together. There's also no shortage of people who want to build robots and no shortage of C# developers who are really into it. So it wasn't hard to start getting traction. One of the big takeaways for us was that rather than spending all of our time struggling to get core systems to work, it just was there and it worked, and we could start building actual business functionality into the robot early. It freed up all kinds of resources and really made the process smooth and seamless. So we started to scale up. We have a large multidisciplinary team to do this. You can't just have software engineers build robots, as it turns out. You need electrical engineers who know board layouts and who can do sensor selection and things like that. Firmware engineers for the microcode on the controllers. Mechanical engineers. Robots are filled with actuators and motors and things like that. And you need to prototype a lot of these things. A linear actuator is very different from a 4-bar linkage, and you spend a lot of time prototyping things. That's just the nature of the business. Industrial engineers, people, obviously they eat with their eyes first, so if your robot is ugly, people will think it is ugly and stupid. Some of the big things that started to boil out early were the fact that manufacturing is a giant process and it takes a lot of time. And so you wind up with these manufacturing milestones that you go through to anchor your product deliverables and to build your software teams around the delivery product. You're going to get a prototype on June 2nd, and you know it's going to have 3 new things than the last prototype had in it, and you better be ready for that when it comes in the door. The other thing you're going to do is a lot of experimentation. There are lots of sensors on the market. There are lots of actuators and motors and variable resistors. There's so many things to play with. So you're going to need a lot of these things. Get your Arduino out and level up, because that's the prototyping platform, and it just works to test a lot of this stuff. Make sure you're spending time establishing test criteria, what you're looking for in a sensor or system, because it makes a difference as to which sensors you select. There's like 300 time-of-flight sensors, and I could pick any or all of them. Which one do I actually want? So we wound up with this guy. This was our test platform. We called him Mars. We made one to start with, which it's not pretty, but it does the job. And we learned really quick that what you really need is a bunch of these, because you're building robots, people need them to do their work, and they fall apart all the time. It's obviously it's cobbled together, but it did the job to help us test the platform and to figure out what works and what doesn't work. A couple of the things that really worked well for us were having 3.3 and 5 volt power rails ubiquitously available on the system so that you could just plug in a new sensor and get it spun up. We picked this sort of prefab chassis because it had lots and lots of mounting options. The other thing we do is we have an acronym in our lab called ABP, which stands for Always Be Printing. We're always 3D printing a new thing, whether it's a bracket or a sensor or a holder or fascia. We're always printing new things in order to figure out what's going to work and what's not going to work. You can see like the time-of-flight sensors that are on the front there. We probably printed 25 brackets to find ones that didn't suck, and that was the closest we got. As we went through this process, there were a lot of good things we learned. There were a lot of highs and lows. One of the first things we discovered early on was you need to abstract away hardware because it's going to be in short supply. It's going to be hard to get. So when you're designing your platform, make sure that you've got enough mocks in place. You've got enough test fixtures in place to not depend on hardware because it's going to be inaccessible or broken all the time. And that's just an expectation you need to set. On the other side, when you start getting your prototypes in for manufacturing, they're really, really expensive, and you're not going to get to mess with them very often because somebody will need it to show off to somebody. So you have to kind of accept that fact. Traditionally speaking, robots are largely a loop with math inside, and that does not make for good object-oriented design. When you move past a control system robot, you can start thinking about object-oriented programming and embracing it again because it does make sense. Again, a great example is a distance sensor. It senses distance. I don't care if it's ultrasonic or time of flight. It's the same problem. Conversely, there are things that will be procedural and algorithmic, and there's going to be 800 lines of code in a method because that's the most efficient way to do it, and sometimes you have to suck it up and do that. You can look away from that or not run code metrics on that if it makes you feel better. Start working with your contract manufacturer really early. We learned this early on in building all of our products. Lead times on parts are all over the map. So currently there's particular capacitors that are at a 34-week lead time. We've got H-bridges that are 28 weeks out. That's a long time. So if you're going to be picking those parts, you better know how long it's going to take to get them, and you better be able to get it aligned with your CM. There's a lot of hard problems in robots. As it turns out, that's why not a lot of people build really cool robots. Focus on those problems early because when you solve them, at least passably so, a lot of the other architecture is going to fit in around that. You're going to have some of these really hard problems around control systems or navigation or the cognitive services baked into the robot itself. And those are pretty hard. Once you've got those solved, you can build a framework and an architecture around those things to support the needs of the robot. The other thing to think about is that the domain is changing very quickly. UWP, robotics, AR, VR, all this stuff sort of coalescing right now. What that means is that there's a lot of new tooling available all the time. There's a lot of new technology available all the time. Embrace it and get on the bus because a lot of that stuff is forward-looking in future, and it may be a little hard to acknowledge it now or to adapt to it now, but the sooner you pick up on that stuff, the better your product will be. As with anything, there are things that were not working so well, the lows. We learned pretty quick when we started to try to break into the driver stack on the 410C in Windows IoT Core that wasn't terribly accessible. The driver documentation is not great, the process is not great, and getting any actual support from the BSPs was difficult at best. They're not terribly helpful. The performance profiling tools that we have against an ARM device in UWP, it's remote, not great. There's a lot of finger pointing when something isn't working right, and the tools don't really help solve that for you. Don't forget that you're still working with the device. In our case, it's we've got an A53, and if you treat it like a server, if you expect it to run like an 8-core Xenon, be prepared to be disappointed. It isn't going to do that. Threads are expensive, and you only have a finite number of them, so make them count. We also have a problem with Wi-Fi deployment and debugging. The 410C is only 2.4 gigahertz, and our network in our lab was made in, as far as I can tell, the 80s. So sometimes Wi-Fi deployment may take 45 minutes for no clear and obvious reason, and you're going to smash your face on the table. That's just part of the process. It's robotics. One of the big takeaways that we had about things that did not work well was around code from the community. When you're running an IoT Core instance, when you're running on ARM, most of the code that you would leverage, whether it's a LAPACK or a BLAS or any of those sort of algorithmic packages you expect to just be ready and work, aren't there. They don't work. They're not compatible. The dependencies they're built on aren't compatible, and you wind up having to write a lot of that stuff yourself. So don't be afraid of that. A lot of these things are open source, and you can go re-implement these things when you need them, but you can't expect to just take the tool off the shelf. It's going to take more time. The obligatory please complete an evaluation slide. Please complete an evaluation. If this was terrible, feel free to tell me that. Lastly, if you want to know a little bit more about Windows IoT Core, windowsondevices.com. Sphero.com if you're looking to see what we're making, see some new stuff coming out. And then if you're interested more about robots, you want more information, you want to build some robots, go ahead and shoot me an email, and I will do my best to get back to you. Thanks, everyone. Appreciate you coming out today.